Okay, with the continuation of our last class, which we have studied so far, we'll proceed to the next content, uh, and that is on the carrier transport in MOS transistor, and especially in the nanoscale. What is the transport behavior in the MOS transistor? So that we need to take into consideration. Now, transport behavior can be mostly here we focus on the electron transport here. Okay, so because the transport behavior, if you want to can if you can able to study in a MOS transistor, then able to we can able to know what actually the aspect ratio or design and channel length, channel width, what are the things we have to design accordingly, then we can consider, because that is very important. So as you can know, so this is a conventional NMOS transistor here, and this is actually the also the MOS transistor. So the three in the three-dimensional view. Okay, so all of you know this one. So, but to just to illustrate this, the schematic here. So as you know, the two N plus regions are there, and we have a gate region, and we have a gate oxide here. If you can see, this is the gate oxide, and we have this source, drain, and gate electrode. Okay, so you know all these things. So but it's a three-dimensional pictorial representation. Okay, so now we'll proceed further. So short channel devices, what are the things we have to consider that we need to that we need to study well, because unless until the device dimension, whatever we want, so that actually depends upon what are the channel dimension which we have in our devices. Channel devices means the effective length between source and drain. Okay, so this is the this is the N plus region that constitute one source electrode, and the another N plus region which we have another electrode, that is drain region, and that effective distance between source and drain is actually our channel length. Okay, now in the on NMOS transistor or the MOS transistor, if we can say, so this channel length is effectively is reduced to a considerable value. But how much channel length we can able to reduce, that actually the main point here. Now, depending upon what actually the channel length, so that depends upon the consideration of transport behavior in our devices. Okay, so as the technology scaling reaches the length less than one micrometer, now second order effect that were ignored in our devices with long channel length, which is greater than 1 micrometer. So due to this dimension that we need to uh, tell in a other way, that we call it short channel devices. So going to the dimension that we call it short channel devices. So short channel devices means the effective length which we have between source and drain, when it is reduced to a considerable value, so that we call it short channel devices. Now, main second order effects which we generally have, that is velocity saturation, threshold voltage variations, and hot carrier effects. Okay. Now, this is actually our source. This is our drain. This is our effective length between source and drain, and we have a gate oxide layer. Okay, generally it is silicon dioxide. Generally, then we have a polysilicon. Okay, polysilicon material. Sometimes we use also metal electrode also. Okay, and this is our P type substrate. So there are three ways of transport behavior we generally categorize. So they are actually three main categories. So they are called, one is ballistic transport, another is diffusive transport, and another is quasi-ballistic transport. Okay. So let's say if L is equal to our channel length, if L is equal to our channel length, and let's say our and lambda is our mean free path of electron. Okay, so what do you mean by mean free path of electron? The average distance covered by the electron for each consecutive collision. So that actually our mean free path. So I think you know all these things. So in our cases, if our effective channel length, okay, the channel length is very greater than our mean free path of electron, then that we call it diffusive transport. Okay, so in our cases, in the case of diffusive transport, our channel length is very greater than, okay, very greater than our main free path of electron. Okay, but in case of ballistic transport, this is very interesting thing, when our channel length is very less than our main free path of electron. Okay, so in that cases it is called ballistic transport. So thus opposite is the case in diffusive transport. Our channel length is very less than our the mean free path of electron, whereas in ballistic transport our channel length is very less than the mean free path of electron. Now, at some point of view, if our channel length is equal or numerically equal to our mean free path of electron, then in that cases we can say that the devices operate in the regime of called quasi-ballistic region. Okay, so that we call it quasi-ballistic. So it is not diffusive, not ballistic. That we call it quasi-ballistic. So the device operates in this region. The transition is called to be quasi-ballistic. Okay. So it's all depend upon what actually the channel length we are taking into consideration. The channel length, that's why is very important. Depending upon what actually the channel length dimension which we have, that is this L. So that determines our transport behavior here. So remember this one. When you say that this device is operating in the ballistic region, that means you can be sure that the channel length is very less than the mean free path of electron. Okay, so normally now which we have is our MOSFET devices, which is very channel length is very small, so that sometimes is used in the ballistic region, you can say. Okay, the transport behavior is governed by ballistic transport. Whereas if the channel length is very greater than the mean free path of electron, that we call it diffusive transport. Okay, so this is the main three transport behavior which we observe in our short channel devices. Okay, so I hope this is clear to everyone. Now let's discuss some terminology so that it will be easy for you to understand well the transport behavior in our MOSFET devices. Okay. Now, this is that is a terminology is called drift. Okay, this drift velocity also we call it. So, what is meant by drift? The process in which the charged particles move because of an electric field is called drift. Okay, so remember the concept of this drift velocity is associated with the electric field. Okay, so that means whenever you think that there is a drift velocity of electron in a semiconductor devices or MOS devices, you can be sure that velocity is associated with the electric field. That means with the influence or with the impact of electric field, there is a velocity is attained by the electron, so that the velocity which is achieved, that is called drift velocity. Okay, now the charge particles within a semiconductor move with an average velocity proportional to the electric field. So here if you can see here, this velocity which you call it, so this velocity is proportional to the electric field. Okay, so this velocity that we call it drift velocity is directly proportional to the electric field here. Now when we have a directly proportional relation between two, so that the direct relationship between this proportionality between velocity and electric field. So we have a proportionality constant will be introduced in the relation. So that proportionality constant we call it mobility. Okay, now if we take into consideration of electron mobility, so this electron this drift velocity of electron will be minus mu n into electric field. Okay, so this is actually our drift velocity of electron. Okay, whereas if the drift velocity of hole is taken into consideration, so this is actually our if Vh is the mobility of whole drift velocity of hole, mu p is our mobility of hole, and E the our electric field. This whole velocity will be mu, Vh is equal to mu p into E. Okay, so all things are the relations are same. Only difference is the polarity we have. In case of electron velocity, we put the negative sign here, and if you take into consideration of whole drift velocity, so this is actually our mu p into E. Now, in these cases, when you find this diagram, if you can see here, that is a collision of electron. If you can see, this electron may be collided with this electron. Again, this collided with electron. So it it follows a zigzag path. Okay, so it follows a zigzag path, and the the average velocity, which is which you can say the average velocity attained by this electron, that we call it also the drift velocity. The because previously these electrons will be moved in a zigzag path. Okay, so this is but when the application of electric field, these electrons will be moved in a systematic manner, and so as you know, these electrons will move from negative polarity to opposite positive polarity, whereas the current will move from the opposite direction of electrons, that is from a positive to negative terminal. So this is actually our this drift velocity concept. Okay, so this is actually the drift velocity is associated with the electric field when the charge particles move under the application of electric field, that we call it drift velocity. Now another thing is that is very important, that is called the carrier diffusion. Okay, now it why it is happened now due to thermally induced random motion, the mobile particles tend to move from a region of higher concentration to a region of lower concentration. Okay, so just like you think that it's a ink droplet in water. Okay, so so that we call it a diffusion motion. Now diffusion means that is a this concentration gradient. That means concentration gradient of electrons. So that means the electrons will move from higher concentration to the lower concentration. So that is actually the concept of diffusion. So let's say there is a higher concentration of electrons in one region and lower concentration of electrons in one region. So the electrons has this ability, or you can say that electrons has these characteristics, that the electrons will move from higher concentration to the lower concentration. So that actually we call it concentration gradient. That is what is the change, the change of concentration with respect to distance. So that we call it gradient. Okay. So just like rate means that anything physical parameter with respect to time. That we call it rate. Similarly, gradient means anything with respect to physical parameter if it changes with respect to distance. So that we call it gradient. So in our cases, in the carrier diffusion, that is a concentration gradient. Okay, there is a concentration gradient. So in that cases, if there will be more concentration of electrons in one region and lower concentration of electrons in another region, then electrons have the ability to move from higher concentration to lower concentration. Now, main important thing is that the which actually very the difference between metal and semiconductor is that, and the current which is flowing in the metal is this because of the application of electric field, and that the current which is associated with it, we call it drift current. Okay, but The difference between metal and semiconductor here is that in a semiconducting material, yes, we also find the drift current concept in the semiconductor, but what is there in semiconductor but not in metal is that we have a diffusion current in semiconductor but not in metal. So diffusion current concept is only you can find in a semiconductor but not in a metal. So that is the difference between metal and semiconductor. In metal, whatever current you just find, that is actually the drift current. Whereas in semiconductor, we have two currents. So one is called drift current, another is diffusion current. Now, drift current is the application of electric field, so which I have just now tell, and diffusion current is the the concentration gradient due to the thermally induced random motion. The electrons will move from a region of higher concentration region to lower concentration. So that actually the current which is associated with this concentration gradient. So that we call it diffusion current. Now, current flow due to mobile charge diffusion is proportional to this carrier concentration gradient. Okay, so this is, let's say P is our whole concentration, and then dP by dx is nothing but our uh, whole concentration gradient. Okay, and what is dP? dP is our, let's say, diffusion constant for hole, let's say, and let's say Jp is our current density. Okay, that is diffusion current density of holes. That means current per unit area, and let's say Q is the charge. So this Jp, that is current density for hole, is directly proportional to the this concentration gradient. Okay, whole concentration gradient. Then in that cases, one uh, proportionality constant is introduced. Okay, so in that cases, this proportionality constant is called diffusion constant for hole. So that we call it dP. So this diffusion current density Jp is called is minus Q dP by dx. So this is a whole current density. Similarly, if you have a electron current density, so it will be Jn. Okay, Jn is equal to Q dn by dx. Only difference is that we have in our cases there is no negative sign, so we have a positive sign in that cases, and the same thing. Only the difference is that we have a electron concentration gradient and electronic charge and electron current density. Okay, so this is actually the cases. Uh, so Jp is equal to minus Q dP by dx. This is our current density for hole, and current density for electronics Jn is equal to Q dn by dx. Okay, so this is actually the diffusion current equation. Okay, so if you can see here from this diagram, we have a semiconducting material, and there is a non-uniform concentration. If you can see, we have a higher concentration here, lower concentration in this region. So the electrons will move from the higher concentration to the lower concentration. So injection of carriers, that we call it injection of carriers in this region. So that if you can see here, the injection of carriers, if we have in this region, so the electrons will move from a higher region to the lower region. So this concept is called our diffusion current. Okay, so this concept is generally we can find in our semiconducting material, and our MOSFET devices, that is metal oxide semiconductor field effect transistor, is governing completely on semiconducting material. So we can find this kind of current behavior in semiconductor. Remember this one. This diffusion current concept only you can find in a semiconductor, not in metal. Okay, so that you always remember. So that is the difference between metal and semiconductor. We need to think, and also we can need to understand. And what is this? Uh, So the unit of mobility, as you know, centimeters per volt second. So similarly, the diffusion constant unit is the centimeter square per second. Okay, if you can find the dimension here, you can find the unit here. You can find centimeter square per second. So whole diffusion constant, the unit is centimeter square per second, and electron diffusion constant unit is centimeter square per second. So I hope this is clear to everyone. So if you can see here, so this is a diffusion example. So this is a linear concentration profile. We have this injection, and the electrons will move from higher concentration to the lower concentration. So let's say this is for a length L, and this is our concentration L we have, and this move from in this direction, in the positive x direction. So this linear concentration profile, constant diffusion current will be, in case of hole, if we take it, so P will be N whole into 1 minus x by L. Okay. So this diffusion current density, as you know, minus Q dp by dx. So dp by dx is our whole whole concentration gradient, that is rate of change of hole with respect to the distance, and dp is our diffusion whole diffusion current, diffusion constant for hole, and q is our electronic charge. So it will be finally coming to q dp n by l. Similarly, for non-concentration profile, if we have varying the diffusion current, we have whole concentration will be n into e to the power minus x by ld. So in those cases, it will be minus q dp by dx. So finally, comes to be q dp n divided by ld e to the power minus x by ld. So this is actually, so for two cases, one is linear concentration profile and another non-linear concentration profile. Okay. So in that case, how the current density will be governed. Now this is actually which I am going to tell. So if you can see here, the diffusion current, how it is actually we can represent. So if you can see here, in this region, we have a higher concentration of electrons here. Okay, and here we have a lower concentration of electrons. So the electrons have the ability to move from higher concentration to the lower concentration. So so that is why the diffusion current is associated like this. So the electrons diffuse from a higher concentration location to a lower concentration location. And if you take into consideration of the direction of diffusion, so it is like this. Okay, in this direction. So in the positive x direction. So this is high concentration of particle, and here there is a lower concentration of particle. So if here with particle we take into consideration of electron here, so the electrons will move from higher concentration to the lower concentration. That means the electrons can diffuse from higher concentration to the lower concentration. So that actually our diffusion current, and that is this is the mechanism of diffusion current concept. And if we can further we can discuss about the diffusion current, then the diffusion current within a semiconductor consists of hole and electron component, because in a semiconductor, as you have two components, one is hole and another is electrons. So this we can represent in this way. So diffusion current for hole. So P is our hole and DIFF is our diffusion current. So diffusion current density, J is our diffusion current density, which is nothing but minus Q dp by dx. Okay, so this is our diffusion current density equation. Similarly, uh, diffusion current density for electron will be Q dn by dx. So this is actually our diffusion current density for electron. So Q dn by dx. Okay, so if total diffusion current density, if we can I can find out, so it will be diffusion current density total. So that means taken into consideration for both hole and electron. So it will be Q dn by dx minus Q dp by dx. So these two relations are actually, if we can combine together, we can find the total current density. So q dn by dx minus q minus dp by dx. Okay. So the total current flowing in a semiconductor is the sum of drift current and diffusion current. So if we can find out the total current, so total current will be uh, drift current plus diffusion current. But each current has consist of hole and electron components. So that means each electron component is a hole and electron component associated with it. So here we have a drift current density for hole, that is Jp drift, that we call the drift current density for hole, and this is drift current density for electron. This is diffusion current density for a hole, and this is diffusion current density for electron. So J total, that is our J total will be our total current density will be Jp drift, is nothing but drift current density for hole plus Jn drift, that is drift current density for electron, plus Jp diff, that is our diffusion current density for hole, plus Jn diff, this is our diffusion current density for electron. So the total current flowing in a semiconductor is now the sum of diff current and diffusion current. So this you should remember always. Okay. So what is the total current in a semiconductor? So that is actually the sum of drift current and diffusion current. Now PN junction, when you say in equilibrium, okay. Now in equilibrium, the drift and diffusion components of current are balanced. Therefore, the net current flowing across the junction is generally zero. So in that case, is our drift current of hole is negative of diffusion current for hole. So Jp drift is equal to minus Jp diffusion. Okay, so this is actually our drift current for hole is equal to minus diffusion current for hole. So Jp drift is equal to minus Jp diffusion. Similarly, our Jn drift, this Jn drift is equal to minus Jn diffusion. That is drift current for electron is equal to minus diffusion current for electron. So total current density will be drift current for hole plus drift current for electron plus diffusion current for hole plus diffusion current for electron is equal to 0. Okay, so this J tot is equal to total current density. Jp drift is our drift current density for hole. Jn drift is our drift current density for electron. Jp diff is our diffusion current density for hole. Jn diff is equal to diffusion current density for electron. So if we can give a total, so it is equal to 0. Now this is very important. The ballistic and diffusive transport, which we have just studied, which we have just now have give a glance on it. So how this is actually the things. Okay, so let's think that this is our the yellow region, which you can see here. This is a electron path. Okay, and this is our scattering center. Okay, so scattering centers can be anything. So like can be like there's so ions, or it can be other scattering centers. So like this, if the electron paths are there, so in our cases, in ballistic transport, uh, there is no actually our scattering. There is no actually scattering, because in our cases the channel length is so small. Our channel length is very smaller than our mean free path of electron. So this channel length is very small. So so in case of ballistic transport, generally there is no scattering. Okay, so ballistic transport with almost no scattering we can think of. Now short channel devices, so generally the ballistic transport is generally governed. So you can think that if the channel length, that is the distance between source and drain, if it is let's say around 2 nanometer or 3 nanometer, that means you can think that the channel length is very smaller than the our main free path of electron. The main free path of electron the channel length is very very small. So you can think that there will be any hardly any scattering center, and if there will be no scattering center, we have a ballistic transport. Ballistic transport, you can think just like a bullet that is shoot from the gun. So it will directly, if the when it is shot from the gun, so directly hit the target, right? In that cases, the bullet won't uh, collide with anything, and it will directly hit on the target. So that kind of thing, maybe you can think that ballistic transport. Okay. Whereas in long channel MOSFET devices, let's say with the channel length is more. If you can think here, here the channel length is very small, whereas in this cases our channel length is high. If the channel length is high, then there can be a scattering center. That means the electrons can collide with other scattering centers. So that will lead the electrons, uh, if the whatever the electrons will come or originate from source, it will at the end it will reach at the drain, but it will have it will collide with some scattering center. Okay, so in that cases our this kind of transport behavior is called diffusion transport. That is diffusion transport. And this diffusion transport is such way that our channel length uh, channel length is greater than our mean free path of electron. Okay, so this is actually our diffusion transport here. So ballistic transport, you can say, is the direct movement of electrons in a short distance channel where our regular scattering is negligible. And generally, the ballistic transport is observed when the dimension of the medium through which the electron travels are much smaller than main free path of electrons. Okay, so this is actually the concept of ballistic transport in a short channel devices. Whereas in diffusive transport, an electron is inducted into the channel and it gets a little way and then scatters and loses some energy and keeps heading towards the drain. An electron may scatter several times before it reaching the drain. Okay, so one part you can be confirmed that in if you have a ballistic transport in a MOSFET devices, you can be sure that the channel length is very very smaller than the mean free path of electron. Whereas in a diffusive transport, our channel length is greater than our main free path of electron. Okay, so here ballistic transport channel length is very very smaller than our main free path of electron, whereas in diffusive transport, our channel length is very very greater than the main free path of electron. As in the main path of electron in case of ballistic transport is very very less than channel length. So in our cases in ballistic transport there is no scattering centers, whereas in diffusive transport we have the electrons will encounter some scattering center. So as the channel length is very very greater than the mean free path of electrons. So just to summarize, so ballistic transport is the direct movement of electrons in a short distance channel where the regular scattering is negligible. Ballistic transport is generally observed when the dimension of the medium through which the electron travels are much smaller than the mean free path of electrons. Whereas in diffusive transport, an electron is injected into the channel and it gets a little way and then scatters and loses some energy and keeps heading towards the drain. Now, an electron may scatter several times before it reaching the drain. So that actually the difference between the ballistic and diffusive transport in a MOSFET devices. So you should know this the difference, that what actually the transport behavior in short channel devices and what is the transport behavior in in long channel MOSFET devices. So you can conclude here in this discussion that in short channel devices, okay, short channel devices means where our channel length is very very less than the main free path of electron. So that actually governed by ballistic transport. Whereas in long channel devices, that means long channel MOSFET, where our channel length is very very greater than our the main free path of electron, then in that cases our transport behavior is diffusion transport. Okay, so that is a trip diffusion transport is taken into consideration. Okay.